Have you ever just sat back and wondered how something like ChatGPT actually, well, thinks? I mean, it can write poetry, it can debug your code, it can explain quantum physics. It really feels intelligent. But today, we are going to pull back the curtain on all that and really demystify the magic. And you might be surprised to learn that it all boils down to one incredibly simple task: predicting the next word. Right, so let's just jump straight into the big question, because this is the real head scratcher that makes these models so fascinating. How can a system whose only job, its only goal, is to guess what word comes next? How can that system write a piece of functioning Python code? It feels like there has to be a trick, right? But it's not a trick. It's actually the result of this incredibly powerful process that we're about to break down. Seriously, that's it. At its very heart, everything an LLM does, from answering your questions to generating that code, it all starts from this one single objective. So if you give it a phrase like, Mary had a little, it's just doing a massive calculation to figure out the most probable next word, which, let's be honest, is almost certainly lamb. And that simple loop of guessing, checking its answer against huge amounts of text, and then updating itself over and over, that is the engine that drives everything. Okay, but for a machine to predict words, it first has to understand them. And since computers don't speak English, they speak the language of math, the very first step in this whole journey is translating our human language into numbers. This is where things start to get really cool. This whole journey happens in three main steps. First step is tokenization. This is where the model breaks our sentence down into these manageable little pieces, like the word dog, or even parts of words like run and ning. Then second, each of those little tokens gets a rich numerical identity. This is called an embedding. And finally, number 3, something called positional encoding gets added. This is super important because it tells the model not just what the word is, but where it is in the sentence. Think about it. The dog chased the cat and the cat chased the dog use the exact same words, but their position changes everything. And this is a really critical point to understand. A token is basically just a label, an ID number for a word. It has no meaning on its own. But an embedding, that's a whole different ballgame. It's a sophisticated multidimensional coordinate. It literally places the word in this vast meaning space where words that mean similar things are located close to each other. So the word dog is going to be way closer to wolf than it is to car. And this is probably the most famous example of just how powerful that meaning space is. Because the relationships between words are captured with math, you can literally do arithmetic with concepts. You take the vector that represents the idea of kingness, you subtract the vector for maleness, you add the vector for femaleness, and you end up right at the vector for queen. It's incredible. This isn't just memorization, it's a learned mathematical representation of abstract relationships. So, to put an official name on it, what we're talking about here is a word embedding. It creates what's called a semantic space. The best way to picture it is like a giant, multidimensional map of language where every single word has its own specific location. And the distance and the direction between words on this map, well, that's what tells the model about their relationships. And that's the foundation for understanding all the context and nuance in our language. A great way to think about this is to compare it to how computers learn to see images, if you're familiar with that. In an image classifier, the first layers of the network might just detect simple things like edges and colors. But the deeper layers combine those to recognize more complex stuff like an eye or a wheel. It's the same idea in an LLM. The embeddings are like that first layer, and as they pass deeper into the model, it learns to recognize more abstract linguistic features, things like grammar, tone, or even sarcasm.
All right, so our words are now numbers. They have meaning and they have position. The next giant leap for the model is to figure out how these words relate to each other inside a specific sentence. And this, right here, is the secret of context.
Let's look at a classic problem. The trophy would not fit in the brown suitcase because it was too big. Now, for us, as humans, it's pretty obvious that it refers to the trophy. But how on earth does a machine figure that out? It needs a way to weigh the importance of all the other words in that sentence to solve the puzzle. And this is where the transformer architecture's absolute killer feature comes into play. It's called the attention mechanism, and honestly, the best way to think about it is like a fuzzy dictionary lookup. For every word it's looking at, like the word it basically sends out a query that's asking a question like, hey, who am I referring to here? Then, every other word in the sentence presents a key, which is like it advertising its identity. And finally, the model calculates a score to see how well each key matches the query, and it focuses its attention on the words that get the highest scores. And you can see exactly how that works here. the query coming from the word it matches the key for trophy with a really high score, an 8.3. Meanwhile, suitcase gets a much lower score of 2.1. This mechanism is what lets the model create these dynamic connections on the fly and understand that in this very specific context, it is all about the trophy. Now get this, because this is a really wild insight from some recent research. You would think the model is constantly crunching numbers and reasoning at every single step along the way. But it turns out, for a lot of tasks, the model kind of defers the heavy lifting. It spends its time gathering all the information it needs from the other words, and then it does the most complex thinking right at the very end, at the position of the final word it needs to predict. It's an unbelievably efficient way to work. So the model has turned our words into numbers. It's used attention to understand the context. Now we're at the final step. It's got this rich, context-aware understanding of everything we've given it. So how does it actually choose which word to spit out? Well, it doesn't just pick one word. What it actually does is generate a probability score across its entire vocabulary, every word it knows. So after seeing the cat sat on the, it might assign an 85% probability to the word mat, maybe an 8% chance to floor, a 3% chance to chair, and so on. The model's final output is actually a ranked list of every single possible next word. And that's where something called decoding strategies come into play. These are basically the rule books, the algorithms that take that giant list of probabilities and actually make a final choice. And which strategy you use can totally change how the model behaves. Let's just compare two of the basic approaches. On one hand, you have greedy search. It's the most straightforward. It just always picks the word with the absolute highest probability. It's safe, it's predictable, but it can also lead to some really repetitive and, frankly, boring text. On the other hand, you have stochastic sampling. This introduces a bit of randomness. It samples from the most likely options, which means it won't always pick the number one choice. And that allows for much more varied and, creative answers. And we can actually control that randomness with a setting that's usually called temperature. You can think of it like a creativity dial. If you turn the temperature down low, you make the model more confident in its top picks. That leads to more focused, predictable answers. But if you turn the temperature up high, it flattens out all the probabilities, giving even the less likely words a fighting chance. This basically encourages the model to take more risks and come up with more surprising text. So we've walked through the entire mechanical process, right? From text to numbers, from context to probabilities, and finally to picking a word. But all of this brings us to the biggest question of all. What is really happening inside this machine? Is it just memorizing patterns, or is it actually learning? This is the debate that's at the very heart of AI right now. Are these large language models just incredibly sophisticated statistical parrots, just a glorified autocomplete that's seen billions of examples? Or, in the process of learning to predict text, are they forced to build an internal, statistical model of the actual world that all that text describes? Now, I know this diagram looks super complicated, but the idea it represents is actually profound. Researchers have shown that for a model to get really good at this simple task of predicting the next word, it is mathematically forced to learn representations of the true underlying concepts that created the text in the first place. Let me say that again because it's so important. The task itself forces a kind of understanding. In order to get better at predicting the next word in a conversation about physics, it has to build an internal model of concepts like gravity and momentum. To finish a story in a believable way, it has to model what characters want and how they behave. That simple goal of predicting the next word turns out to be a powerful driver for learning a genuine model of the world. And that really just captures the power and the mystery of these systems, doesn't it? We started with a machine that just guesses what word comes next, but we've ended up with a system that, just to get better at that guessing game, is forced to build a coherent internal model of reality. If this is the kind of power that emerges from just guessing, it really makes you wonder, what's next?